In this video, I want to spend some time discussing the concept of multicollinearity. It comes in two forms. First, there is exact multicollinearity, which is really just being able to perfectly predict one of the x using a linear combination of the other x's. That means that one of the x is a linear function of one or more of the other x's. Then there is strong multicollinearity, and that's simply when there is a strong correlation between two or more of the x's. Let's start with a discussion of exact multicollinearity. Again, this is when one variable is a linear combination of other variables. For instance, here x1 is exactly equal to a constant plus a coefficient times x2 plus another coefficient times x3, and so on and so forth. That means that if we add x1 to our regression, there is no new information available on which to estimate parameters. We already have all the information by looking at x2, x3, and the other variables. If you try to run a regression where you have exact multicollinearity, either the software will tell you that we have a multicollinearity issue and it will automatically drop one or more of the variables, or it will just return an error and say it cannot run any regression with this dataset because of multicollinearity. Another issue is that interpretation is impossible in this case. Here is an example. Say we want to run a regression of life expectancy on height in centimeters. In our sample, we find that the estimated coefficients are 130 for the intercept and minus 0.3 for the slope. Then we are wondering if we should add height but in inches to the regression. Height in inches is proportional to height in centimeters. It's just height in centimeters divided by 2.54. If we take both of these variables, which are collinear, we'll find many solutions to the regression equation. For instance, we'll find that we could have the first regression equation, so 130 minus 0.3 times height in centimeters, minus 0 times the height in inches. So the 0 cancels out the height in inches, and we have the first regression equation. But we could also put 0 in front of height in centimeters and have minus 0.76 times height in inches and find exactly the same results. Or we could have minus 1 for height in centimeters and plus 1.77 for the height in inches. So there are infinitely many solutions, and the software will not know which one to pick and to show you. We also see that we can have an interpretation because we have one interpretation for each of these different equations, and if we don't know which one to pick, we don't have one to interpret. Multicollinearity is also the reason why we cannot have an indicator variables for each of the categories of a categorical variable. For instance, in one of the dataset, we had a categorical variable which will tell us if a movie passes or fails the Bechdel test. And if it fails, there were many subcategories for why it failed. For instance, it could be that there were no women in the movie, that they didn't talk to each other, or that they talked only about men. We can see here that the variable OK, which means it passed the Bechdel test, is equal to 1 minus each of the other categories. In that case, it's a linear combination, and so if we try to run this in the software, it will automatically drop one of the categories, which is the new reference group. When you don't have perfect multicollinearity or exact multicollinearity, you might still have a strong multicollinearity. This is when you have a strong linear relationship, but not a perfect linear relationship, between two or more explanatory variables. In that case, we have one of the x's that is well approximated by a linear function of the other x's, plus some error, so it's not perfectly predicted. Remember, parameter estimates represent the effect of a covariate on the expected outcome when you hold all the other x's constant. If two variables tend to always move together, we can't really estimate the effect of each on the expected outcome, because one never stays constant when the other moves. For instance, let's say that you're looking at predicting sales of cereals. Your company wants to increase the price a little bit, but they also want to reduce the quantity that you find in each of the boxes. In your dataset, every time your company has looked to increase profits before, they have increased the price, and at the same time, they have reduced the quantity. It makes it really difficult to tell if the change in sales was due more to the price that increased or to the quantity reduction, or maybe a bit of both. So unless your variables don't always move together in the same direction, you might not have sufficient variation between the variables to separately estimate their effect. When we have a strong multicollinearity between two or more variables, the software will still run the regression and will not return an error. However, we might find that we have increased p-values, so now we can tell if each of the variables that are correlated are significant or not. We will also have a larger confidence interval. In our previous example with the size of cereal boxes and their price, we will not know if there is a strong coefficient on the price or on the size or an average coefficient on both. The solution is to remove the offending covariates, so the covariates that are correlated. It should not affect too much the R-square because we still have a lot of information in the remaining covariates. However, the adjusted R-square should increase because we are lowering the penalty for additional variables. However, we have to be very careful when we interpret the result. Let's say that in our previous example, we remove the change in quantity inside each cereal box. We might find that the price has a strong effect. However, maybe the effect was entirely driven by the change in size. So when we interpret the result, we might make a wrong decision saying, oh, the price has a strong effect, let's just change the size of the cereal box. One way to find the offending variables in case of multicollinearity is to measure the variance inflation factor for each of the variables. It just gives you a score that measures the amount of collinearity for each of the variable, and a value greater than 5 means that you have a strong correlation between this variable and the other ones. Here, as an example, we have a regression of the car's MPG, so miles per gallon. This is a fuel efficiency, on the displacement, the horsepower, the weight, and the rear axle ratio, denoted DRAT, of each car. We see the formula is just a linear regression of these variables. There is no quadratic term and there is no interaction. We find the following results. Then we decide to look at the variance inflation factor for each of the variables, which is represented here on the top right. We find that for displacement, there is a very strong inflation factor. And if we look at the correlation matrix on the left, we find that indeed displacement is heavily correlated with each of the variables. It has a correlation of 79% with horsepower, a correlation of almost 90% with the weight, and a negative correlation, but with a strong magnitude of minus 0.71% with the rear axle ratio. So we might decide to remove displacement. And when I rerun the regression, I find that it doesn't change the R-squared at all. It goes from 0.838 to 0.837, so we can't even notice a change. And the adjusted R-square actually increases from 0.814 to 0.819. Then we find that it decreases the standard error of correlated variables. This is what we see at the bottom, and before we had a standard error for weight of above 1, and now it went down to around 0.8. And finally, it also decreases the p-value of the correlated variables. So weight went down from 0.3% to 0.03% for the p-value. Be careful again, don't make interpretations necessarily based on these coefficients. We might have removed displacement, which could be a very big factor on the outcome, and find that the other variables are strongly effective or are strongly significant, even though they might be the main reason for the current outcome.